Okay, let me just what we did yesterday. We demonstrated a maximal function, and we are on the way of doing the Science theorem for dimensions 3 and higher, which doesn't have work with development as only is a maximal function, and the rate of these that we are very motivating those are the problems. And we are connecting that by doing a frequency decomposition of the Fourier transform of the measure sigma without taking the relations. Okay. And so if we can, where the kj equals 0, it's at the low frequency terms, and we already saw that this is bounded by the handling of the maximal function. So if we can prove that for high frequencies, we have a geometry decay, there exists some exponent, positive exponent, as we have here on decay, then we can sum over all frequencies, and then we can run. Okay. And then we saw a bunch of reductions that what they help us is to obtain the L2 estimates, the L2 theory. So if I fix the time and it's considered some fixed time you want, then we saw by Beltran theorem that by knowing what the Fourier transform of the spherical measure is, in particular how it decays, then we can get this the decay requested by the Fourier transform of the measures. I didn't prove this formula, but I debated it. And we are not going to use the fact that we can get more precise asymptotics. We are only going to use the decay. That's going to be a theme during this week. But next week we will actually use this. Okay. And we also saw how by and this here the solution used for the body for the compute in a range between 1 and 2, and then we saw how this implies a maximal function estimate when we are localized between 1 and 2. That was this Heller and this Heller argument at the expense of losing an extra power 1/2 here. So now the exponent we get is just d minus 2 over 2. Okay, which we can see that for equals to fails to be found. Okay. And then we also saw how to put the time scales together by a weaker version of the probability theory, and therefore we can have the estimate of the okay. Are there any questions about this? Okay.
So far you've just used just the decay of Fourier transform.
Just the decay of Fourier transform. Yeah. So now that we have the theory, what we are going to prove is some bad one theory, and then we're going to. Okay, so this is gonna the main estimate is gonna be the problem lemma. Nice. With automatically as we work, okay? Okay. So what is this lemma? This little lemma telling us, maybe let's just apply why this lemma was for the but this lemma is telling that this is a L1 normalized bound function at the scale to the j. Okay, and we are only taking the spherical integration. So the 2 to the jd that we have to kill off because that's the magnitude of this, only to the j d minus 1 we have killed off. And then there's one extra 2 to the j remaining, which is this one with that's the magnitude distribution. Okay. And away from the unipolar stuff. Because there is a measure, and this is essentially the scale localized the scale to 2 minus g. That's what it tells us. Let me apply this as a corollary. I have then is a the volume by the j. I have this bad estimate of width as okay, and this because once I have this is a rapidly decreasing function. So when I'm going to take then the t dilations and I'm going to convert with my function f, that's going to be dominated by the Hamilton maximal function. Okay, so using that lemma, then if I now dilate this for p5 p, okay, equal 1. So now I just dilate this, okay, and then there should be more. That's the limited value. We will take. So then having this L1 estimate with loss 2 to the j and L2 estimate with loss with gain minus j t minus 2 over 2, then interpolation between L1 and L2 tell us that there exists an epsilon p positive if p is precisely the balance section. And I'm not going to do that. Okay, but you can verify that that's they match at the right place. Okay, so let's go with the proof of these little lemmas. Therefore, the proof of stack theorem is going to be concluded. So
You've also done this on H1 instead of beta 1.
was that?
But you've also just observed that you get it bound from H from L to H1. For the second growth.
Okay. Yes. Okay. So so here I'm gonna just use that beta here. This is a function which is simply to become a support. So therefore, beta the imaginary transform has as much decay as I want. So that is just try. Then B sigma y, and I iterate in y. Oh, it's here. Okay, we're gonna repeat that. And now I'm gonna split this integral according to the magnitude of this. So and I'm gonna let it go this. So let me that's 1 equivalent. This is subdominant with respect to 1. Okay. 2 to the j x minus y. This is the 1. And then the next is sum here. And to the thing with j x minus y is yeah. Theoretically decomposing the sum. Okay. Maybe let me go this little main integration. This is I'm gonna call it as my n1 x. This I'm gonna call s n of x. Okay, the -1 is because I was starting from the 0. Okay. Okay, so a few observations on the size of this. Okay, so okay, so So the spherical, when I'm gonna take a spherical measure, at some point it might be convenient to take a spherical measure of this domain because in this part, this quantity is not apporting me any decay, right? So I can think of this as just being a constant. Okay, so I'm gonna end up with having to measure this as this set. Okay, so what's the worst magnitude that this can have? This might be a wall of radius 2 to the minus j, but I'm taking the spherical integration, so it's 2 to the minus j d minus 1. Okay. Okay. And then I have also the other guy, it's the same region. This is now, I have already decomposed, so this is a constant effectively on this domain. Okay, and now this is, I can do the same argument, no? But now this 2 to the j is continues on the other side, no? So it's 2 to the minus j plus m, right? But I only want to do that if I can, if I'm only taking a portion of the sphere. You know, I also have a trivial bound, which is that it's just bounded by 1. Okay, because it's also always going to be a subset of the sphere. Okay, so I only have this, and then so I'm going to put it so that it's the K. So then I can see that this is good. And then this is good. If J is greater than M, and otherwise. Okay. And also note that these terms, for these terms to contribute, in principle, my x can be anywhere, right? But if x is very far, there are going to be some terms that will contribute or whatsoever, right? So in order for that to contribute, we have that x is less than x. Depending on where I am, I have a control over x minus y, and the y is always a point within the sphere. So this is always controlled by 1 from this one plus depending on where I am. So it's going to be minus 0 plus 1. Okay. So with all these now in hand, I can just start manipulating these intervals, okay, and see what I end up with. Then okay, so here, as I said, now this is constant because I have radically decomposed this, and I have 2 different bounds depending of whether I am here or here. So I'm going to split the sum up to j, and then from j on. Okay. And in this case, we have to do an AD, right? So that's over there. And then this is about 2 to the n, right? So I get that then I have minus m capital N, and then I have the measure of this object, which I know is the minus j minus n. Okay, and then the other terms I have exactly the same, but then I'll have this. Okay. Okay, but I can try to remember a little bit more where I am, right? So as I said, this only happens if the x is in this board of radius to the n minus j plus 1 when the n is large, okay? or just an ball, unit ball, or twice the unit ball, if it is small. So I can put here for free. And then for the ratio in the two and the last two. Okay, so now let's rearrange all these J's and M's constant that appear here. So J, D, and then minus J, D minus one, so then I get here substitute to the J, which is 1. And then now I have the sum from minus 1 to J, and then I have minus N, and then I have capital N, and then now minus D minus 1. Okay, so if N is large enough, sorry, capital N is so large enough, this is very good, right? Okay, and this one will go. It's already 1. Okay, and then the second term. I want to use that I have, I want to obtain that I have decay at the end, right? That when X is very large, that it does actually contribute. And I can use this decay, this 2 to the minus n decay to trade it off with X decay. Okay, that's the observation. So I can put here for 3 if I want 1 plus X, then to the capital M, then 1 plus X to the capital M. But now I can use that. I have control for this X because I need that bond, right? I have this thing here. And the N is large, so this is the term that dominates. Okay, so I can actually replace this numerator back to be M minus J minus the constant. And now I have here to do JD, and then to do another N, capital N. Okay, now I can get rid of people. Okay, so the first term is already good. Okay, as I said. Okay. And then for the second term, I have okay. Check. Here a term that is on a decay, which is what I want, and then let me put together the J's and the D's. J, okay. So what I want is to do J. So then you bring it back to the J, and then I have the JD. So this becomes to the JD minus 1. And but I have a 2 to the minus J and to kill it off. Okay, and then I have the 2 to the N. Here we create capital N minus capital N. Yeah. That's there. Okay. So so now this is if I choose the capital N to be larger than the capital M, and this is decaying, right? And therefore I get the first term in here. So then the M can be the little m can be replaced by the little j. Okay. So M and and when this reconciliation can cancel, and then I can choose the end to give out this loss. So any questions about this? So with this, that is the dilemma. We also had another version that in case away from a spherical shell, right? I'm used to do spherical angle of with spherical J. But that gives us an conclusive of that figure. Okay. So what next? You can okay, there is a theorem that I mentioned at the start, and then we already saw or discussed that circles and spheres they have different properties in terms of tangencies and that are an enemy, and then Jonathan is discussing the circular case, right? What else can we say about these objects? And one reason why I like spherical averages or maximal cellular averages in more general version is because it can guide us to many aspects of harmonic analysis and many different ideas in harmonic analysis can be related to this object. And so in particular, I'm going to focus on how classical techniques like Calderon-Zygmunt theory also play a role in the study of these objects. And I'm going to try to exemplify that through the study of the lacuna spherical maximal function. So that's going to be the next topic of the project. And how this got also later on, things about lacunary means when we have here not p equal 1, but some sort of line. Okay. But today I'm going to focus on this. So by the lacunary means, I just mean that my radius will all be of the form 2 to the power k. Okay, and I take supreme over all k in the integers. Okay, so then theorem. Theorems in Callisto Calderon. 79 seen independently by 49 bucks at the same time or around the same time. We have the population years. And we did a different code. And yeah, we have comments for all here. Okay, so one thing that you might ask is that why can we now enlarge the range of p's? Before we have this threshold, the already minus 1, and now I'm saying that this holds for all p greater than 1. Okay, so let's try to remember what was the example that we gave. And here we just take as my test to be the characteristic function of the unit ball or some function adapted to the unit ball, right? And if we were at a certain distance x, then we took as a radius the modulus of x to hit this ball. Okay, that's the example. Okay, so now what values are admissible now? Now only 2 to the k powers of 2 are admissible. Okay, so if we want to take this, okay, I can only do it if x is equal to 2 to the k. Okay. But this is asking for too much of a restriction because I don't need to exactly go here to 0. I could also arrive here at 1/2, for instance, if I want it, right? And I will still capture the same measure. So I don't only get here when modulus of x is equal to 2 k, but I also get that in a tiny ball of radius, 1/2 if I want, okay, of dyadic lattice points, and then this example is radially symmetric. So then, what is when I am obtaining that S of that? This is I'm putting here. Okay, so I am getting this if the x, let's say, when we run the algorithm, okay, this is the normally the function of the programming. Now, when that is happening, it happens, and this has to happen from positive case, okay, from 1 to 0. So now I have my measure, okay, the measure of any of these guys. But these guys, they are over 1, and this is of radius 2 to the k, right? So this is 2 to the k d minus 1. That's a measure of every of these shells. Okay, and I have that's e to the minus k d minus 1 times p. Okay, because I'm raising this to the power p. So you can see that as soon as p is greater than 1, this is convergent, right? So this example is telling me that now a priori it is plausible to go down to p still greater than 1. Okay, for p equal to 1, this diverges, but in the weak type case, this would be replaced by a soup, and therefore this is not even a perfect example for a weak type one. You can see that in here I was not sticking to lacunary. What means is that instead of putting here a ball of radius 1, I'm putting a ball of radius 2 to the k, and therefore this will become 2 to the kd, and then of course the d over d minus 1 comes up again, right? Okay. So then if we compare to what we just did, so in there we have a really good L2 bound, right? And this L2 bound cannot really be improved any further. But what we interpolated with is a sort of bad L1 bound, okay? And then we stop in the middle. So in order to go down to p greater than 1, now what we need to do is a final analysis of L1, right? Something that doesn't lose a constant to the j. Okay? That's more or less what we need. So we need a final analysis near p equal to 1. And I'm not going to give the original proof of Calderon on Portman advice. At least the one like Calderon is the one I'm a bit more familiar. That one is more sort of more direct, and it's based on doing the Calderon using the composition of the function. And he actually obtained also like a sort of like Oryx type space bound. But what I'm going to give is an argument of dual Picochea and Rubio de Francia which is a much more general argument, and it calls for not just spherical averages, but also for compact measures which have some Fourier decay. The timing of epsilon decay is good enough for these two faults. So it applies in greater general. Okay. So let's do the proof. Well, let's start doing the proof. Okay. And the fundamental idea, this is I think this is from 8 of the 792 year. And one of the ideas that was going on around the time is to we start with a measure and let's try to approximate that measure by a nicer measure. Okay, the nicer measure is going to have cancellation. Okay, and then let's try to exploit cancellation as it has been exploited in the theory of Maximal. And then the difference of that approximation is hopefully going to be controlled by a little bit or whatever. Okay, so let's introduce a nice function. Okay. With y, okay, and we define a new measure mu, which is going to be my spherical measure, and I'm going to subtract this new function here, okay, which I'm going to think of it as a measure, and I'm going to put the average function, the average value of the spherical measure at 0. Okay. So then, okay, sigma is a spherical measure, so sigma is completely supported. Then phi here is also completely supported. So the mu has compact support. Okay. And it also has cancellation. Because okay, mu hat of 0 is psi hat of 0 minus psi hat of 0, phi hat of 0, but phi hat of 0 is equal to 1, so therefore this cancels. Okay. Of course, you have to the same value. Okay. And the property is that it has no worse Fourier decay than my original value sigma. Okay, because my phi here is completely supported, so it's Fourier transform decay as much as I want. So also mu hat of psi is governed by the hat of sigma. Since I have of sigma is okay. So now the idea is to replace the sigma by the nu when I'm so then we are going to study this one to compare. Okay. So I'm gonna add and subtract this side, okay? And when I subtract it, I get the new. then I get the other term, the term. Okay. And is that any logic to do that? And the answer is no, because now this guy this function phi is the same infinity convex support. So in particular, it is dominated by any variable decreasing function, and then the high the maximal function when I get those items. So this is less control value. Because that's a constant, right? There is less control value. The maximal function of f. At the next, which satisfies with LP bounds for opening. Okay, that's fine. So I only need to focus on this guy. So I haven't lost anything in this passage. And now for this guy, I'm gonna control it by this square function. Okay. So if I could also return this directly, but it actually holds a stronger estimator. Also for the square function. We need a stronger estimator. The other day we already saw in Tom's talk that when we are modeling square functions, this sort of appearing historically, right? This is exactly known. And we already saw that we can use random functions and then use that from a singular interval bound when we have randomized signs. Okay, so in order to prove that this guy is only for all p between for all p greater than 1, okay, which again we only need for p close to 1 really, because we already have the two modes, so I can focus on the rest p between 1 and 2. So by a random function argument. And because it already appeared the other day, I'm gonna do it. And we want to show that here these are plus or minus signs randomly chosen. Okay. And then okay. Okay. Oh. Oh, so it's where the E are plus or minus ones. Okay. Like what we say. Okay, so if I were just looking at p equal to 2, I could bound this directly, but I mean, what I'm interested in is in lowering this for p close to 1 as much as possible. And for that, I'm gonna introduce frequency decompositions. Okay. Introduce frequency. So this might become a new K, but I'm trying to be consistent that it's I might go past remember this mean is when a cutoff to keep the indexes I want, right? And I'm just doing for instance, I just choose I have here a minus K and then a free index J with a right overall index. I'm just doing it because for scaling property, for scaling at myself, I do this way. Okay, this is maybe an unfortunate notation because this means now this is where the conflict starts, right? Because this was coming from new sub t, so that's why I was keeping it to the k. But now this is also meaning a 2 to the k. This a 2 to the k. So at this point, it might be clearer if I just have this, okay? And then the origin, we are not in the we are in the lacunary case, so I can index this by k and forget that the lecture yesterday, okay? And then this becomes more clean. Okay. And I'm gonna then call this as I have a sum. I interchange the sums in J, and I'm gonna then call this my kernel scale value. F, okay, or it's a frequency piece, where Kj is the sum of the many case of the new okay, I just realized this. Okay. So now we prove okay. 2 on 1, calling this 2 on 1 because it's another 2 1, it's another 1. But the other one is easier, so we will start with the other 1. Easier things. I prove that this in L2 is pretty good, okay? It decays with the frequency. Doesn't matter if it is high frequency or low frequency, we can with the validity. And then for one, we'll have a problem with the volume. So then we have an improved L2 inequality for its frequency peaks. Okay. As I said, the L2 argument we are going to use here, we could have actually used directly to bound the whole square function. Okay. But when we fix a frequency peaks, then we get decay. And this is useful because then even if I have a bad bound at weaker 1, okay, then it's here with logarithmic loss. I can interpolate it with this one and I can get geometric decay for all p's greater than 1, and then I can sum and obtain the boundness for bigger than 1 for my fraction. Okay, so if I can put this, this is how we develop. So here, and two again, this is going to be helpful because then I can go to Fourier side and I can use Fourier decay properties. And you'll see that here, the two really, we need, I put 1/2 here, but we need really minimal decay. As soon as we have an epsilon at L2, then I can interpret that I'm good. So this is why this is not only for spherical lattices, which have like a very good decay at L2, but only an epsilon degree at L2 would be enough for example. So this is why this is so general. Okay? So let's start with 2. Okay. of my parameter. That's what I get when I go to level. Okay, that it was my multiplier. Okay, and now I have that these are frequency little projections. Okay, the J is fixed, and I'm running this sum in K, so I have a normality, right? The sum of the columns. You can see here now I'm already getting the random sign, so the estimate that I'm gonna obtain is uniform on the choice of Maximal. Okay. So now let's look at the behavior of this new K. So the new we knew that it behaved like the original measure, okay? And well, in our case, this has minus b minus 1 over 2. But as I said, any decay is fine. Okay, so observe then that we have for that bound over there, then using the spherical average, well, this is the same as this one, right? And dilating this by 2 to the k. So then the equation again is 2 to the k modulus of psi 2 to the power minus b minus 1 by 2 in 2 to the k more psi. This is bigger than 1. Okay, that's why that's the data. Okay. If this is smaller than 1, then a priori, if I had continued with the spherical measure, then I would just be able to say that this is bounded by 1. Okay. But I have introduced cancellation. Okay? So it is here where we are using cancellation, because then when I am bounding this, well, I can put it back. Given I can introduce for free the value by 0. Yeah. And then I get this is bounded by 2. Okay, so then I use this whenever this is small. And therefore I have a winning inequality of both cases. Okay, so here is where this approximation has been established. Okay, so now we go back here and say that. Okay, then this is going to be controlled by the minimum of the k times mod psi. Okay, but then okay, what's the size of I can do it this time. This is 1, this is the other one. And then square. Okay, but I have that my frequency psi is about 2 to the j minus k, right? That's what my frequency is. So so this becomes this by is equal to j, and this by also equal to j. And once this is now k independent, so this can go outside of this sum, and then the sum in k, I can use it to put together the frequency pieces again. Okay? So all in all, I obtain like this is the minimum of 2 to the j, and 2 to the j, b minus 1 over 2, and then I will this is to another square, and this is together at the square of the function. Okay. So you can see now that now if the j is negative, I'm going to use this one, and if the j is positive, I'm going to use this one. Okay, so in any case, I always get here. Okay, so I'm going to. Okay, so let's now go to the thermal one. Okay, with thermal one. Okay. So for the weaker one bar, okay, these are weaker one inequality, and here we have a kernel, and the observation is that these are going to be Calderon-Zimmer kernels, satisfying the Hormone condition, but the Hormone condition conflict is divided loss. Okay. And then by applying Calderon-Zimmer theory of the shell, we obtain this equation. Okay. So, so we go into 25. Okay. Because the AJ has to satisfy the so okay, so I feel very okay, so let's do it. Okay, we have the KJ, we have the expression over there. Okay, for the kernel. So if I apply what it is, okay, then we have epsilon here is UK the half straight plus the decimal one and which will be accepted as I get the option. Yes. Let me use the scale here, okay, to just get rid of this of the K scale in the measure. So this K cancels with this K, but therefore this becomes then becomes dilated by the case. Okay, so scaling. Okay. Okay, so I'll use that. So then demonstrate it in front of everything. Then the new now has is that with the scale, the new frequencies are scale J, Okay. And then we are going to be evaluating that's minus y. Keep it okay. Same for this other. We just convenient to clean up as much as possible with the levels. Okay. So now here I have a 2 to the KD, right? That I can kill off, but the x is divided by 2 to the KD, so I can do the change of variables, x goes to 2 to the k, and then I can kill this off, and then this also gets killed off, but survives in the y. Okay, so I have clean up a lot more this, but also here in the line of integration. There was 2 to the k here, so it becomes 2 to the 1 minus k 1. Okay, so so with this, let me kill off the signs. So I end up with something here, then outside. So I'm ending up with this. Now reading from those signs, so like about this and about it. Okay. And these I'm gonna go. That's okay. With one of these comments. And we want each of these terms forever. Okay. But here there's an observation that if I set y equal to y prime, then this term ik becomes ik minus 1. And this estimate I want to take it for all y. So I can, by doing that process, I can reduce all of these estimates to just bound the term I1. Okay, by carrying on that change of variables. Okay. Or in other words, it means that for every k, I can assume that my y has a specific size, that my y is in a unit, it's in a unit scale. Okay, between 1 and 2. Okay. Okay, and then what are the control estimates that we don't have on item? Okay, so let's examine the term. Okay, and well,
How much time you need to finish?
I don't know. It might take more than 5 minutes, but at least I want to say a couple of words of the idea, and then so that I can sketch it very briefly tomorrow morning. Okay? Yeah. So, so here we have BJ little baby cat. Okay, so the data can be anything, and I'm saying is integer, right? This is not always possible. Okay. So I'm going to do this picture because it to me helps me quite a lot when I think about these things. So this is roughly constant at the scale to the minus j. Okay, and then we have a second scale going on here. So the y here is between 1 and 2. Okay, so it means that the y here is at a scale 2 to the minus k. Okay, but the k can be is also an integer, so this minus k doesn't really matter, it can be anywhere, right? So again, we have several possibilities. But this is the 2 to the minus k lands here. That the 2 to the minus k lands here. Okay. And then as I said, it could well be that during the scale is here, or in blue, that during the scale is here. Okay, all these options. Okay. So let's just forget about the red bar. Okay. Let's just assume that we are in this situation. So anywhere, always that we have this kind of situation, we have a little belly cutoff here, and then we have some variable which is small and at a scale much smaller than the little belly projection, then we can get a gain here coming from the cancellation, and is in the difference of the scale between those two objects. Okay, and this is Cardinal-Simon theory, right? This is the idea that always goes in Cardinal-Simon theory. We use the cancellation to get a gain in the difference of the scales. Okay, so here is when one uses cancellation. Okay, then there are also but this is not going to be enough, right? Because it could well happen that the 2 to the minus k is also much larger than 2 to the minus j. Okay, but if it is way larger, we are hoping typically to get some rapid decay, and that these terms they don't really contribute too much. So, okay, so we are in that situation. And then there is because of this possibility of having that the j is positive or negative. Normally, the rapid decay one needs here the k to be negative, so we are in a very big scales. Okay, that's what one uses this rapid decay. So it could well happen that we need here some estimates that are here in between up to unit scale. Okay, these estimates in between, that it's only logarithmic many estimates. Okay, it's only j scales. And here we are just going to use trivial estimates because these are always satisfied O1 estimate. We are interested in satisfying decaying estimates in the parameter j. Okay? But j and k, the difference between j and k. But here we might not get anything other than a trivial estimate. But how many terms are there in j? There are j, right? So how many k terms are j is fixed? How many k terms are here? So this would be this would be this picture of one here. So the case that are larger, but now good. Okay. I'll end up doing that tomorrow, but those are the ideas. We are small, we use cancellation, but we are very big with capital K. Maybe between we have some loss, which is that loss that appear here.
Thank you, David. Any questions? Well, I got one. Yeah. For the ordinary maximal, what is the endpoint itself? What's the vehicle?
So I'm going to discuss more about that after these results. So that's going to be part of tomorrow's lecture. So currently it is open whether it could be tight or not. So this is an open question.
It's an open question.
It's an open question. So this also serves to advertise it, this course. And I'm actually going to present tomorrow a substitute result at the endpoint, which is at H1 to weak L1. So that was first obtained by Mike Priest in data analysis paper. He obtained several variations of Calderon theory, and one of them is also that one. But I'm not going to present his proof. I'm going to present a proof by Jim actually and Andrea Silvio, which is much simpler and adapts to a very general setup. So there is this H1 to beta 1, and then there are other endpoint estimates in which the spacer 1 is replaced by a little larger space, okay, between an L1 and L1 plus epsilon with the type L log L and so on, and in there's still work which is being carried. I think the current best record is due to Ben Carosa and Laura Plavek, which improved on a previous result of Jim and Silvia and Tao. They added some extra log or something.
The expected result is good.
There is no good example. Yeah.
Okay.
Yeah.
But it's,
Yeah.
any other
It makes sense,
questions?
we thought we had approved it. But we never made a mistake. Models.
If no more questions, then thank you, David, and then we have a break. We start